Let's look at complex impedance, and in particular, let's look at it for an inductor, and then I will assume that you can go ahead and derive that if you want to justify to yourself that these impedance formulas that we're using for inductors and capacitors and resistors are what we say they are when we're working with sinusoidal steady-state circuits. So here we have impedances of R, L, and C in general. Those we are concerned with when we have sinusoidal steady-state conditions in our circuit. What we want to do now is look at this generalization of Ohm's law for an inductor, where we have the voltage across that inductor is equal to its impedance times I sub L bar. By the notation that we're using, V sub L bar and I sub L bar are phasors, and then in general, Z sub L, the impedance of the inductor, is going to be a complex number or a complex expression. What we want to do then is find what Z sub L is equal to. And what we will do then is figure out what an expression for V sub L is in terms of its phasor relationship, what is I sub L bar in terms of its phasor relationship, and then take their ratio to find the inductor impedance. Let's look at what we know. We know Eli, and that's our mnemonic for remembering that the voltage of an inductor in the time domain, or the voltage across an inductor in the time domain, is L di sub L dt. And that's what we're going to use then to derive these relationships for the impedance of the inductor. Suppose we start with this sinusoidal steady-state value for our inductor current, and let's give it a magnitude of I, and assume that it's a sine of omega t. When we go to convert that to a phasor form, we actually want to always, for convenience, work with one or the other, sine or cosine. We typically work with cosine, and sine of omega t is simply equivalent to I cosine omega t minus 90 degrees. And that's because we know this idea of the sum of two angles, or the cosine of the sum of two angles, is just the cosine of those A and B plus the sine of A and B. We know that the cosine of 90 degrees is 0, the sine of 90 degrees is 1, consequently this is sine of omega t, and this is the formula that we were just using, that the sine of omega t is cosine omega t minus 90 degrees. If our if our current through the inductor is a magnitude I sine of omega t, based on Eli, or V is equal to L di dt, then we know that V sub L of t is just L times the derivative of I sub L of t, but the derivative of sine is just cosine, and we now have I cosine omega t times the derivative of the argument of the cosine, which in this case, the derivative of omega t with respect to t is simply omega. We can now rewrite that as omega L I cosine omega t. That's in the time domain our voltage with respect across the inductor. Let's now convert those to phasor forms. We had I sub L of t was I cosine omega t minus 90 degrees, and V sub L of t because of V is equal to L di dt, was omega L I cosine omega t. The phasor form then of I sub L of t is I sub L bar, which is simply I at an angle of minus 90 degrees. The phasor form of V sub L is omega L I at an angle of 0 degrees. With this generalization of Ohm's law, which is V sub L bar is equal to Z sub L I sub L bar, we now know that Z sub L is V sub L bar over I sub L bar, or Z sub L is now going to be omega L I at 0 degrees over I at minus 90 degrees. We can now simplify this. The angles subtract when they are in this division relationship, and we end up with the impedance of the inductor under sinusoidal steady state conditions is omega L 0 minus a minus 90, or omega L at 90 degrees, or in the more conventionally expressed form, that's J omega L for the impedance of the inductor. All you have to remember relative to how did we get J omega L from omega L 90 degrees, remember that 90 degrees in this complex plane, if this is our real part and here's our imaginary part, this has a magnitude of 1. We have a magnitude of 1 at 90 degrees. That's what this represents, but that in rectangular form is simply a real part of 0 plus so we have real part of 0, and we have an imaginary part of 1. And that now is how 1 at 90 degrees, which is 90 degrees for an angle, is equal to 0 plus J1, which is just equal to J. Using that, we find that the inductor impedance is J omega L, and I think you can similarly derive the relationship that Z sub C is 1 over J omega C for the impedance of a capacitor, and Z sub R is simply R, because R, or resistor, does not have any time or differential relationship between its current and voltage.